So good afternoon. In this second live session, this is a doubts clearing session. Whatever doubts you have, please post in the chat box and we will take those up one by one.
Good afternoon, everyone.
In the meantime, some of the questions that were there in the discussion forum, we will take those up.
So first we will take up the question which was related to the hydrogen use in IC engine. So one of the questions says that hydrogen simulation related to IC engine, which software can be used for that. So typically, whichever IC engine related software you are using, typically they are designed for petrol or diesel. So, but one of the important aspect of hydrogen as a fuel is the difference or the very high flame speed when we use hydrogen as a fuel. So there are two software which are actually used for evaluating the flame speed of hydrogen or any different fuels in the spark ignition engine. So one is the open source software is Cantera. So we'll put it in the chat box also. Cantera software, which is open source, and another which is the licensed software is Chemkin, which is comes within the bundle of ANSYS. So Chemkin or Cantera can be used for evaluating the your flame speed, and you can compare the flame speed of petrol versus hydrogen, and there you can evaluate that how much of lean mixture you need to operate to obtain the flame speed which is similar to the petrol, because that is how we are supposed to run it in the existing spark ignition engine. So, any questions?
So on the chat box is a mock session. Actually, we are having problem solving sessions every week by the TAs. Monday and Tuesday, we used to have that session. Yeah, software names, we will be writing that and then we will post. One of the questions in the discussion forum is, why are we still using energy intensive storage options, such as type 4 tanks for storing hydrogen? Yes, you are right that type 4 tank storing hydrogen in compressed hydrogen form, wherein we store at either 350 or 700 bar for vehicular application. This is an energy intensive process and the infrastructure is highly capex oriented. So definitely the use of metal hydrides or the solid state hydrogen storage, as is being asked, will be beneficial. But currently this is at the laboratory development scale, and now some of the systems, they have even been demonstrated at a prototype level. So some demonstration have been like installing these tanks onto forklifts or for mining equipments. Even some of the two-wheelers also have been operated, two-wheelers and three-wheelers have been operated using this type of storage. And if we use this type of storage, because these are low pressure storage, the expensive compression requirement or having refueling stations at such a high pressure, which should be even higher than the tank pressure, will be very much lowered down, but that may take some time. Question paper pattern you are asking about, so it will be computer based and multiple choice question. So special training related to the software.
Okay. Is there any special training related to software from your side or any case studies available? So there is no special training as such, because this is a software. You just don't need training in using the software, but also it requires understanding of the complex kinetics and the evaluation of flame speed. So that is not in the purview of the our overall course. It will just require knowledge to use the software. That itself will take around 3 to 4 hours of lectures. So maybe in future, maybe there will be a course which will be float on IC engines for alternate fuels. So that can be explored by the interested candidates. So, and they will be having that detailed sort of analysis and methodology for evaluating the claims for different fuels.
So one of the questions from discussion forum is, what is the area in which I can contribute to the research on lowering the cost of hydrogen storage? So in terms of, if we talk about the three different areas, three different modes of storage in compressed, as we know, the compressor development. So there is now work which is going on non-mechanical compressors. Even the solid state storage, which you have learned, the metal hydride based compressors are also available, like research is going on. So this is one area of research. Another one is now even people are going beyond type 4 tanks, type 5 tanks to going to 1000 bar. So that is another area, but as already mentioned, it will be more energy intensive and expensive, capex oriented. In terms of liquid hydrogen, the areas could be, because we have already learned in the course, there are a lot of boil-off losses. Now, how these boil-off losses can be reduced, and even if we cannot avoid it completely, what that lost or evaporated hydrogen can be, how that can be tapped back. So that could be another area of research in terms of hydrogen storage in solid state form. And also you have asked about the simulation, how to proceed for research work. There are various tools we are using in our group. You can use whatever software you are comfortable with, NSYS or COMSOL, for designing or for optimizing the geometrical parameters or performance indices. And in terms of the reduction of cost in solid state storage, there are challenges with respect to materials. Purified materials, as we have also learned, that 1 addition after point 1 digit more addition, it causes a lot of cost increase, because the purification process, it requires a lot of infrastructure. So when in case of storage, solid state storage, the materials is the challenge, and the canisters design. So these are the other aspects wherein you can work in the case of hydrogen storage. What are the recent advancements in the field of metal hydride? Different materials have been looked at. The basic objective of those materials which are used for storing hydrogen have been to get more of hydrogen storage capacity, to make these cyclic processes, that is charging and discharging, faster by improving kinetics, and also making the operational conditions, that is the temperature or pressure, as per the requirement of the utility. Maybe it may be a higher pressure for compressor, a higher temperature for thermal energy storage, or for backup power, it could be optimum conditions, near ambient conditions of temperature and pressure. So that is what people are researching about in terms of materials. The recent advancements have been, there are different type of materials which people have looked at. Recent interest is on high entropy alloys. Then there are complex hydrides, chemical hydrides, which have high capacity. Metal hydrides, these have been studied for long, and now there are different materials, their combinations, compositions, people are studying on. Different designs wherein you can have of canister, wherein you can have better heat transfer. So different simulation options to see what design could be better, and then how that will perform in utility. That are the different work which people are doing. So there have been advancements even in India. There have been earlier demonstrations at Banaras Hindu University, wherein they have demonstrated vehicles. These were 2-wheelers on motorbikes, or even 3-wheelers. They have demonstrated such metal hydride based tanks. And now the research is towards taking that further a step ahead.
Yeah, so there is one question which says that we are finding moisture content in the engine manifold, exhaust manifold, which can lead to the cracking of exhaust manifold. So actually, we don't have to worry about that. because H2O, which is a product of combustion of hydrogen, is not only present when we are using hydrogen, but it is also present when we are using any hydrocarbon-based fuel. So, for example, if you are using petrol or diesel or methane or CNG as a fuel, bulk of H2O comes as a product of combustion. So, and in all the cases, it comes at very high temperature. So, our engine exhaust manifold is already designed to handle the exhaust gases with high amount of moisture content. We won't say the moisture, but it is like a superheated steam. So that particular thing is already the material being used in the engine exhaust in the current vehicles are good enough to handle the exhaust of the hydrogen based engine combustion. So I hope it is clear. Combustion products are not very different from the conventional fossil fuel based systems. And another question which says that how hydrogen vehicle become more advantageous than electric vehicle. If EV is charged to 35 kilowatt hour, then vehicle will run about 400 kilometer. What about hydrogen vehicle kilometer per kg hydrogen? So when we look into hydrogen as a fuel for vehicles, then there are two perspectives. One is you can use hydrogen as a fuel for IC engines. So basically the engine will be IC engine based vehicle. And second will be, it will be fuel cell based vehicle. So when we look into the fuel cell based vehicle, your overall sort of an energy conversion device is a sort of a electrochemical cell. And the efficiencies are quite high. But when we come to the IC engines, there the efficiency is very much limited because of your second law of thermodynamics. It is very, very difficult to design an engine which will go to 30-35% of thermal efficiency. And when we look into batteries or fuel cell, we can easily achieve twice the efficiency of the IC engines. So just as a thumb rule, depending on the size and category of the vehicle and the way you drive, the efficiency of the IC engine based vehicle varies a lot. But just as a thumb rule, we can say that typically if you have an IC engine based vehicle running on hydrogen, you will get half the mileage compared to same energy being stored in batteries or hydrogen being used through fuel cell and then running a motor. So IC engine based vehicle will give you roughly 50% of the given range. Okay, the follow-up question is, we are finding water in liquid form in exhaust manifold for hydrogen engine. Okay, so I will suggest you, whenever you switch on your engine in a very cold condition, not too cold, even in the normal condition when the outside temperature is 20-25 degrees or so, you switch on the vehicle, especially the cars, and observe it for another 5 minutes. Observe the tailpipe. You will see the water dripping out of the tailpipe, even in the conventional vehicles, which is running on petrol, diesel, or CNG. So it is not something very unique or new phenomena. Only amount thing that, like say, I'm using a CNG based car. So it will take all the exhaust manifold to heat up first. So until and unless it is very hot, the water molecule or whatever the superheated steam is coming out from the exhaust will suddenly cool down. All the water H2O molecules will condense and you will see that the water is dripping out. Even you will see the white smoke, which is like the saturated steam coming out of the exhaust pipe. And once the exhaust manifold or the tailpipe is totally hot, more than 100 degrees, 150 degrees or so, then you will see that there is no white smoke, no water droplets will come out. Same is the case with the hydrogen-based vehicle. So hydrogen-based vehicle, it will not give you a liquid water continuously. Once the exhaust pipe will get sufficiently hot, your liquid droplets will just vanish. And the same thing, I just suggest you to observe a tailpipe of any car. So when you switch it on in a cold condition, observe, you will see the same droplets will come out.
So one more question which was on the discussion forum was about the coning effect. Coning effect, it is found in the underground hydrogen storage. Now what like if you have an aquifer and you are injecting another fluid, that is in this case hydrogen with a high pressure into the ground, so there will be a coning effect which will be observed because water will be displacing from the point where it is interacting with the liquid, and that point it will be displaced. So that is like pressurizing. If a pressurized fluid that is injected into a filled tank, so the same effect will be observed here. That is the coning effect.
So, any study available for salt cavern storage in India?
Yes, there is a study. Maybe what we will do is we will post that on through the discussion forum. This is a paper which is by Professor Upadhyay. And there is one more paper which is onto the geological storage by an IIT Bombay group. So we will post those references into the discussion forum.
Ma'am, there is one question from a candidate which says that I am a research scholar and I am working on hydrogen storage in metal hydride. Can you please suggest any composition that I can work upon, or is it possible to conduct any experiments in IIT Bombay?
Composition, actually, it depends upon many things because as I have already mentioned, metal hydrides have that beauty that you can tune the properties based on the composition. So until and unless you, I have an idea like which applications you will be using it for, it's very difficult to tell. And then requirements has to be a priori decided, and then accordingly you can tune the composition. Regarding equipments, like some of the facilities we can, like, depending upon the availability, yeah, you can utilize the facilities which are there at IIT Bombay. You have to write to me and then we will. Please post your questions onto the chat box.
So there is one question where a candidate would say that I understand end-to-end efficiency for green hydrogen generation to its final use, example fuel cell electric vehicle, is still lower compared to alternate fossil fuel options. What is your opinion in this regard? When green hydrogen route is likely to become economically viable?
That is a very good question, and in fact, everybody is looking forward for it. So it is said that when the cost will drop to $2 per kg or even below, then it will be comparatively equivalent to what we are using the fossil fuels of today. So when at present through various routes, if you see, we have seen the hydrogen production, it is still compatible with the fossil fuels using again the route which have a fossil fuel based origin of production. But then when it comes to green hydrogen, economies of scale will definitely bring down the cost. There are different projections that we have also seen because now the different governments, they are coming up with policies and implementation strategies wherein the economies of scales will favor the reduction in the price. So electrolyzers, like for country like India, we have manufacturing is being promoted within the country so that the hydrogen cost would come down rather than importing the electrolyzers.
Exam pattern or question pattern? That's a common question.
So exam pattern is, yeah, I have mentioned, maybe some of you would have joined little late. This will be a computer-based question wherein there will be multiple choice questions. And all these will be whatever being taught from you have learned in the course. So nothing like from outside the course. And there is a pattern, like certain portion will be from the assignments. And so that is the regular pattern for any of the NPTEL course. But it will be an MCQ based.
Okay, so there is another question where product gas is used, or maybe I think Tejas, you are trying to ask about the producer gas, which we discussed on the gasification process. So basically, producer gas is used directly coupling to the engines for power production. Typically, if we look into the history of evaluation or evolution of the gasification system, it started with the direct application of gasifiers and producer gas-based engine for vehicle application. But it was the time when the fossil fuel availability during the Second World War was very low. But currently, when we look into the economics and the safety concern with respect to producer gas, which also has carbon monoxide in it, being used in the vehicles in the running condition, and if some accidents happen, then all those concerns are there. And plus, it is not practical or economical compared to the other conventional sort of fuels. So currently, the major use of producer gas is for either for thermal application, like replacing producer gas for industrial heating, replacing natural gas or diesel or the furnace oil, and in the power generation systems, where agriculture waste or the carbonaceous waste is being used to generate producer gas through gasification process, and which can be used directly into the engines. So engines have been designed, and not only the IC engines, if it is a very big systems, gas turbines have also been designed to run on the producer gas. So for if it is a less than 1 megawatt of power plant, then typically IC engines are used as a power producer. And if it is a more than 1 megawatt of system, then gas turbines are used for generating the power. So I hope the question is answered. Okay, so as I suggested, in this particular course, it won't be possible because it will take a significant amount of time. But I'm also planning for floating a course on IC engines and use for IC engine for alternate fuels, which involves the green fuels and hydrogen and producer gas also. But you'll have to wait for that. Once I float, you can take that course, and then maybe we will be covering all these aspects. So Toyota recently announced ammonia engine. Is IIT Bombay working on developing such engines? So yes, so IIT Bombay also is working. So there is one professor in aerospace department and one in mechanical department. They are working on ammonia as a fuel for IC engines and for other sort of combustion systems. But yeah, it is still in a very nascent phase, as we can say. And not only Toyota, the major thrust on ammonia being used as a fuel is for the marine application, where the big marine engines can use it, which are mostly run on the big ships are run on gas turbines, where they use diesel as a fuel. So they're replacing it with ammonia because it will have high energy density and the carrying capacity will be good when it comes to the marine application. When we look into the land application or the small vehicles, ammonia has some issues which has to be tackled, especially ammonia being a corrosive gas and it has a negative health effects when we inhale it. And when we look into the engine application, there is a small amount of unburnt fuel always comes out when we have especially the spark ignition engines. So we can't avoid it completely. So you take any fuel, like petrol or CNG or hydrogen, which are being burned in a spark ignition mode, it is very difficult to burn it completely, and small amount of ammonia also comes out. It irritates and damages the lungs. So if there are many vehicles on the road, then it will be much more detrimental to health compared to soot or carbon monoxide emissions. So, but it is not something that a challenge which can't be tackled. People are looking for designing a new type of engine, new safety norms, but ammonia definitely researchers are looking to convert a gaseous hydrogen into some liquid fuel as a hydrogen carrier. So ammonia is one of the favorite among them, apart from DME, which is dimethyl ethane. People are also looking for organic hydrogen carriers. There are a lot of options researchers are going on. Ammonia, because it has a very good supply chain usage, handling, and other storage sort of standards available. So ammonia has come out very fast as far as engine demonstration has come. But there are many other hydrogen carrier liquid fuels are there, which we will see in another 5 to 10 years.
Low temperature water gas shift actually, so we have seen that water gas shift reaction is an exothermic reaction. And after steam reforming, whatever gas we are getting, we have to cool it down. Now, when you are operating, still the operating temperature is 350 degrees. So there is a limitation because thermodynamically you have to lower down the further the temperature. So it is, however, dependent upon whether you are using low temperature water gas shift or not. Ideally, it is you can extract more of hydrogen and convert syn gas into hydrogen and CO2 if you add up one more step. But when it is PSA, low temperature water gas shift, we are not using. It is high temperature water gas shift and PSA. Or if it is solvent based removal method, then generally we have both these stages and then solvent based removal and methanation process.
Yeah, so another question is there is hydrogen fuel more preferable for heavy duty vehicles and electric one for light duty vehicles? So actually, you would be listening or hearing these quite often that this type of sort of energy device, whether it is diesel, petrol, or electric, CNG, or hydrogen. So there is I would say it is a big misconception, especially because when we look into the evaluation of these new generation engine, we are still in very new very nascent stage. Just to give a comparison, when we look into diesel and petrol engines, the design of diesel engine and the petrol engine makes them very suitable that it is very difficult to design very big petrol engine. Okay, so that's why most of your heavy duty vehicles, you will see they are predominantly diesel engines. And especially small engines, it is very difficult to design a small diesel engine. So maybe in India, we have never seen except Bullet 350 or Bullet 500, which was a diesel Bullet. Apart from that, any two-wheeler which you will see on running on diesel. So they're predominantly petrol. But that has come after decades of R&D, and there has been a sort of a distinguish between which type of fuel which is suitable for which type of application. Now, when we look into electric ones, it is being said that it is suitable for light vehicles, light duty vehicles, for the reason being the range. But as we have seen in the last 10 years, the battery capacity, its energy density, and its cost has tremendously improved. So it is very difficult to say right now whether 10 years down the line, there won't be any good sort of or economical electric vehicle, which will not be a truck or a long range bus. So it is very difficult to say at right now. And the same is for the hydrogen. Hydrogen is actually a spark ignition engine. So spark ignition engine, designing it a very big spark ignition engine is a limitation. that's how it gets compared to a petrol engine, which is also a spark ignition engine. But the flame speed of hydrogen is very high. So that's why it is easy to design big engines using hydrogen as a fuel and a spark ignition as a source of ignition compared to petrol. But again, it won't be suitable to say that designing a small hydrogen engine is practically difficult or not viable, because right now what hydrogen-based IC engine-based vehicles that we are seeing are predominantly four-wheeler or cars or the light-duty vehicles. So hydrogen technically will be more suitable for both light as well as bigger trucks and buses. It won't have any limitation like petrol. And similarly, with time, with the reduction in cost, improvement in the energy density, battery may come in a big way for long range trucks and cars. So we'll have to wait and watch.
There's in fact, a question related to consultancy help from IIT Mumbai. You will have to identify the faculty working in the area of like green hydrogen, whether you want it like, and then you have to contact the professor. You can.
And maybe Tejas, we would suggest you to sort of take it offline. You can sort of contact us separately, and depending on your requirements, we can also suggest you if some concerned professor in IIT Bombay, they are working on those areas, because green hydrogen itself is a very big domain. Production, storage, usage, utilization, safety, and all those things. So many different professors are working in different aspects. So maybe it won't be appropriate to discuss in an open forum right now. So maybe you can contact us separately. We can discuss and take it forward. So not an issue.
There is one question. Hydrogen storage related major challenges with respect to automobiles in the present.
Storage related challenges. Actually, there are already tanks which have come up, compressed hydrogen tank, but most of those automotive application, the storage form has been in the compressed gaseous form. So the challenge that remains is you do not have infrastructure for fueling those tanks, because what you require is hydrogen refueling station. So sale of those vehicles which are having type 3 or type 4 tanks, they have to be refueled using some of the hydrogen refueling station, and that is highly capex oriented infrastructure is required. And since you do not have very or you have in the country one or two gas refueling stations, so the sale will not increase. So this is coming like going round and round, because you do not have infrastructure. People may not buy cars which are based on hydrogen refueling. And if you do not have some sufficient demand, there may not be sufficient hydrogen refueling stations. So it is like a chicken and egg problem, but to some extent it has to be resolved with support from government. And in fact, a confidence will be required that it's going to help in a longer way, so that more of hydrogen refueling stations are located, at least on highways, where you can get more of refueling stations. And then the automotive sector may see a increase with the compressed hydrogen tanks based vehicles. So that is, the infrastructure is not there at present. Maybe there was a question, certain part of it was related to the range of a vehicle. So it's Like roughly, if you have a light duty vehicle, a four-wheeler, a car, in that case, roughly the range is like 100 kilometers you can drive 1 kg in 1 kg of hydrogen. So that is roughly the range. So usually we require about so the tanks which are designed are to store 5.6 kg of hydrogen.
Yeah, so now the question has been asked, what is the ideal compression ratio for hydrogen combustion engine? So actually hydrogen has a very high sort of a octane number, a very good fuel because of its very high flame speed. So we can go for very high compression ratio because its self-ignition temperature is also very high. So these are the properties which makes it a little better fuel compared to what we say petrol when it comes to the efficiency. So we can design compression ratio of hydrogen engine even more than what is you get for the diesel engines. But technically, there is a sort of a practical problem that if we go for very high compression ratio, then overall energy being spent in the compression and the overall accessories required and all, the cost and power required, work done, it gives a lot of issues. So typically, around 20. Around 20 is the compression ratio that automobile industries they look for, especially when we have hydrogen or methane or CNG as a fuel. The same is with the CNG. CNG also has a very high self-ignition temperature, so we can go for very high compression ratio when we are using internal spark ignition mode. So, but you won't see very high compression ratio more than 20-22 because it becomes a little impractical. The vibrations and the amount of strength that you need to give to the engine, that increases, the cost increases, the engine becomes very heavy. If the engine is very heavy, then your overall mileage will reduce. So you have to make a sort of a break even or optimum design. So for the optimum design, roughly around 20 compression ratio is the ideal one for hydrogen or CNG type of categories of fuel.
So there is a question related to recalibration. So actually we have discussed a whole range of hydrogen sensors and they vary in terms of the response time as well as the sensitivity. So usually the frequency should be higher, but then it depends upon how sensitive that and what is the volume percent in which it can sense. So as we have also seen, there are two different types of monitors. In fact, we will say one wherein you have to monitor the concentration. There you have to deal with larger volume percent of hydrogen. And then there are sensors which you have to be very accurate. So that also the range, it is different for different types of sensors. We have discussed several types of sensors. Usually frequencies you have to identify that when it is so it has to be checked from time to time that when it is sensing, giving a false alarm or not, and then immediately you have to calibrate it back. Yes, definitely safety is of prime importance wherever you are handling hydrogen, whether it is at the point of production, safety or utilization. You have to have those hydrogen sensors, and time to time you have to check whether they are not giving false alarm or they are in fact you are not, some at times it may not, the alarm may not activate also. So that has to be tested from time to time. As such, you cannot have a uniform frequency for all the type of sensors.
Yeah, so as you rightly said that the typically hydrogen or the compression ratio is slightly lesser than diesel, but typically it is not the limitation. It is not the limitation, and I would suggest you to look into one of the cars that was developed by BMW long back, not the recent one. The long back, I think it was 2015 or even before than that. So it was an IC engine based vehicle and BMW, and it was much more having higher compression ratio compared to the conventional diesel engines. And also it was thermodynamically, it has a much better efficiency compared to a diesel engine. So it is not a limitation. As I said that the compression ratio is a factor or cap based on the self-ignition temperature. So we have to design diesel as a compression ignition engine, so we have to have a minimum compression ratio, and that minimum compression ratio is typically in the range of 14 to 16. Otherwise, diesel will not self-ignite. But when we use hydrogen as a fuel, we have to see that we are using a spark ignition. So we are not allowing the hydrogen to self-ignite because self-ignition temperature is very high. So we can go safely, but we don't go for high compression ratio for petrol because it will self-ignite because it is a hydrocarbon fuel. It has a low self-ignition temperature. It will self-ignite, but hydrogen doesn't have that limitation. So we can go for higher compression ratio. So technically there is no limitation. Only the practical limitations are there. And when automobile companies, they design sort of a new generation of engines, you will see that there will be a different categories of engine. One will be the very heavy duty engines which are used for trucks or marine application. They will be very slow moving and low compression ratio. When you look into the faster cars or the sports vehicle, you will see a very high speed and high compression ratio to juice out as much as power from the fuel. So there you will see that the high compression ratio are being used even for the diesel vehicles, especially the heavy SUVs. They will have a high compression ratio and high speed. Same is the case with hydrogen. So comparing hydrogen, which are currently in production, with something which is the highest compression ratio of diesel engine, which is in the market, may not be appropriate. If you look into that BMW, I will suggest you to look into that car. Maybe I will post it in the discussion forum, the model of the car, and you can look into that. It has higher compression ratio compared to the conventional diesel engines that you see in the similar category of vehicles.
So there are a couple of questions. One is related to separation of hydrogen from LOHCs, LOHCs and ammonia. And so there are different types of LOHC. Usually the method to separate is, these are thermal decomposition methods like we have seen for the chemical hydrates. The bonds are broken and you are getting separated hydrogen and the other secondary products. And similarly, they have to be regenerated. In India, there are organizations, this is Bureau of Indian Standards. They are now looking forward along with even the PESO, they have taken lead in coming up with the different standards, and there are different documents which are also available. Metal hydride, what metal hydride is mostly used for hydrogen storage? So there are two conventional hydrides, although the newer materials are also researched wherein there is a slight modification in the composition, and then these are tested for, but the important thing is those materials should also be recyclable, and usually the number of cycles these are tested is 1500. That is a minimum. So the conventional metal hydrides are iron, titanium, and lanthanum nickel 5 with dopants like cerium. These are the conventional metal hydrides, but there are many more metal hydrides which are being looked at. These are BCC based alloys, but then their regeneration and the capacity fading has also been observed. So we want some alloy which has to sustain for at least till the tank lasts. So that has to be tested. So initial testing should be for 1500 cycle, although expected is that it should be working for more than 1500 cycles. So in India, like as has very rightly been pointed out, use of hydrogen as an energy carrier is important to reduce the fossil fuel dependency, import dependency, and there is a lot of work which is going on in alternate membranes, because we have the membranes which are being used, the catalyst which is being used, these are the major cost components in an electrolyzer, and also that definitely the balance of plant. So there are different work which is going on in terms of finding the alternate membranes, because there are certain membranes which are in fact only one supplier, and because of their monopoly, the costs are higher. And precious metals being used in as electrocatalysts, the cost of these electrolyzers are high. So the major research which is going on is to find out an alternate membrane, which could be used in place of, like, if it is PEM electrolyzer, Nafion is the conventional membrane which is being used, and platinum is the catalyst. So there are different work whereas they use different molecules, polymers in fact, to make those membranes. PBI, like one of the name I can give. And there are different groups working in the country which are developing these membranes. And these will be, once developed, these will be definitely cost effective.
About renewable energy co-production for green hydrogen in present scenario as well government policies.
So if there has been recently certain incentives schemes like that has come up from the Ministry of New and Renewable Energy, which is now the governing agency to look after the National Hydrogen Mission. And there are certain incentives for both, like it is being produced, manufacturing, as well as being green hydrogen being produced. Now, definitely co-production here in that is being favored, but these are all incentives in terms of like the pricing, reduced pricing, and there are policies. So you can go through that SITE program, which is SITE scheme, which is already there on the MNRE website. Therein they have announced what sort of, how much production capacity and manufacturing capacity. Based on that, there are incentives being announced.
When we are using spark plug, is it really required to have a high compression ratio? So actually, spark plug usage and high compression ratio, technically it is not linked. So when we need to have a compression ignition, like for diesel, then definitely there is a link between compression ratio and type of fuel. So high compression ratio is required, essentially required when we are looking for diesel-like of fuel, which requires compression ignition. But when we are doing a spark plug for ignition, then the prime importance here is to look at the type of fuel, what is its octane number or the reactivity of the fuel, and the self-ignition temperature. So we should not compress it too much so that it gets self-ignited. So that we have to reduce, we have to see and check. So that's why your petrol engines are not designed for compression ratio more than 10 or 11, because if we compress it more, it will self-ignite before we try to ignite it by spark plug. But when we look into fuels like CNG, methane, or hydrogen, they have a very high ignition temperature. So there the compression ratio becomes irrelevant, because it is much, much higher than any standard fossil fuel for which engines have been designed for. So even if you go for a compression ratio of 30-35, they will not self-ignite. So that's why when we are using spark plug, it is essentially because it doesn't have a property which will make it a good fuel for compression ignition like a diesel has. So when we try to burn it in a compression ignition mode, it will just blast. So we will have a blast if we try to do that with hydrogen as a fuel. But that's why spark plug gives a controlled combustion process. The flame will propagate from the top dead center from the spark plug till the piston. So that depends on the flame speed or the reactivity of the fuel. And that gives a control over the combustion process. So that is why hydrogen, being a very flammable, very highly reactive fuel, so spark ignition is the most suitable way. And here the compression ratio doesn't have any sort of requirement from the fuel perspective, but from the efficiency perspective now. More compression ratio, more thermal efficiency. So we prefer to have a higher efficiency. That's why we are going for higher compression ratio. I hope your question is answered, Karthik.
You can post, if you have any other query, you can post on the chat box. So if no further doubts, we are also like close to the end of the session. If no further doubts, then we can close this session. Thank you for joining for this session.
Thank you. Thank you to all, and all the best for your future sort of Evaluation.
All the best for your exam of this course as well.